Good morning, everyone. We'll be starting class in 1 to 2 minutes time. Good morning, everyone. And today's lectures are going to be focused on completing the IIR filter designs that we started on Monday. In particular, we saw on Monday's lecture, we matched the time response using the impulse invariant design. So in today's lecture, we're going to be looking at how do we match the frequency response using the bilinear transform design instead. As well as, once we finish with this particular lecture, the next lecture will move on to IIR Examples, which will basically give you an idea of the type of problems you would expect on your final exam and how to go about solving these problems in particular. And finally, then we'll move on to problem set 3 with the select questions from My Learning to do live. And we'll start examining how to approach the solutions to these problems in particular. Alright, so let's get started on today's lecture. So, just to shortly recap, in Monday's lecture, what we did, we matched the time response using the impulse invariant design to design a digital filter based on an analog filter prototype. What we're going to be doing today is that we're going to be matching the frequency response using bilinear transform to design a digital filter using that analog filter prototype, and we're going to see how the bilinear transform differs from the impulse invariant design in this particular aspect. So we're going to go back to our relationship between Z and S here, and if we rearrange this equation to make S the subject of the formula, we see S here is equal to ln Z divided by T. Now, if we need to evaluate this, it's very difficult to substitute this in for any equation with S and try to get this S equation back into terms of Z. So we're going to have to do an approximation here for this ln function that's existing here. So we basically use a first order approximation for the exponential function using the Maclaurin expansion. And what we see here is that in using the Maclaurin expansion, we can actually approximate this ln function here and the exponent into terms of Z accordingly. So in doing this approximation here for Z, where it's 1 plus STS divided by 2 divided by 1 minus STS divided by 2 here, we can basically say S here is approximately equal to 2 divided by TS of Z minus 1 divided by 2 divided by TS multiplied by Z minus 1 divided by Z plus 1. That's after we do some rearranging of the equation here and so forth and whatnot. And in generalizing this, we can say that this 2 divided by TS here is equal to some constant value C, and we just keep the Z minus 1 and Z plus 1 as is. And we're using this substitution here moving forward for our bilinear transform evaluation. So in doing the bilinear transform, like I mentioned before, this actually matches the frequency response. What we need to analyze here is how do the differences between using the analog filter and the digital filter representations, what are going to be the key differences there. So in the analog filter, we go from -FA to FA, which is basically representing our analog filter frequency range. And this can actually vary depending on the design and so forth. But because it comes like if we're sampling the frequency of the analog filter here and to creating our digital filter, this FA from negative and positive maps to -f of S on 2 to positive f of S on 2, and as of such, from a variable frequency design that we have for the analog filter, we go to a fixed frequency design with regards to the digital filter. Where f of S here is basically represented our sampling frequency that we use to sample the analog filter frequency as required. Now, remember, in using the sampling frequency here, we also need to make sure that we avoid the aliasing effect. So we want to make sure that we use at least twice that of the original signal frequency, in this case the original filter frequency range that we have here. And for really good results, we'll use up to 4 times or more as required. So the general objective is just to map this analog filter frequency here into a digital frequency range. So we can either use positive powers of Z for our S substitution here, or we can use negative powers of Z. Either one is fine. Typically what people do is that they use the positive powers of Z, they finish the substitution, and they get the entire equation in Z, and then they transfer it back into its causal form with negative powers of Z only. And if the question does ask to transfer it into standard form, you will be required to transfer it into negative powers of Z as required. So typically, using the filter equation, which is going to be h of S, we substitute S equals to C multiplied by Z minus 1 divided by Z plus 1. I want to transfer this h of S equation into h of Z accordingly. So what this substitution does basically, and mapping the analog filter frequency f of A to some digital frequency f, what we need to observe mathematically is that when we start applying the limits for these frequencies here as accordingly, we see here that if we say at the analog frequency here, and we substitute in for our S component, so we see that's j omega A, and then we can expand out the omega A into 2 pi fa. And we know our Z equation is mapped to e to the power S T of S, so we can put in our S component here, which is j 2 pi f T of S. And we can substitute this in accordingly into our S equation where we had Z minus 1 and Z plus 1. If we rearrange and simplify this, we can make the analog filter frequency here the subject of the formula, where we can map our analog filter frequency here to our digital filter frequency as a function. So in general, what happens here is that we need to get this f of A equation that we use in particular to solve for how do we obtain our required digital filter frequency represented by f here accordingly. So this equation here is going to play a key important part into solving for our bilinear transform. In some particular cases, because we have the analog filter frequency and the required digital filter frequency and the sampling frequency, this means that we'll be solving for C here accordingly, which is required for the substitution for S. Now, recall that 2 pi f divided by f of S here, where f here is going to be our cutoff frequency, and f of S is our sampling frequency, this also maps to our digital filter frequency as required, which is capital omega. So we can rearrange this equation into a shorthand version, being f of A is equal to C divided by 2 pi tan of 0.5 capital omega. And this mapping that we see here is the mathematical proof for showing that the analog filter frequency can map to a desired digital filter frequency using this constant C here. And the extrapolation here is given by this point, where f of A is the analog filter frequency cutoff, and f here is the digital filter frequency. F of S here, as required, is the sampling frequency. Now note, because this is a trigonometric function, that there's going to be a non-linear relationship between the analog filter frequency and the digital filter frequency. And this is basically if we watch the limit evaluation of the analog filter frequency and how does it map to the digital filter frequency. When both are equal to 0, when f of a is equal to 0, the digital filter frequency will go to 0. But however, as f of a tends towards positive infinity, the digital filter frequency will just tend towards positive pi. And if f of a tends towards negative infinity, the digital filter frequency will just tend towards negative pi. So from having this infinite frequency range in the analog domain, it maps to a finite frequency range in the digital domain. And this effect is what we refer to as warping. So the design steps that we do regarding transferring the analog filter prototype into its digital filter representation using the Bilinear Transform is that we need to have the analog filter prototype to begin with. We need to match the analog filter cutoff frequency and the digital filter cutoff frequency using f of a equation here to solve for C. So we calculate C using this equation here. Once we have C, we can substitute for S into our H of S equation using the bilinear transform to transform H of S into H of Z. And we're going to watch an example here as to how this can be done. So this question here basically is similar to a question you can expect on your final exam that will expect you to use the bilinear transform as required. So we're going to see here that we need to design a digital filter using the bilinear transform for H of Z at 3 kHz. So this is actually going to be our digital frequency here. And to match to the appropriate analog filter H of S at omega A equals to 4 radians per second. Now notice this is omega here. And this means if we want to get to f of a, omega A is equal to 2 pi f of a. We're given the analog filter prototype equation, which is H of S here. And we're also given the sampling frequency f of S, which is 12 kHz. But we need all these components here before we proceed with the bilinear transform. So in matching the analog filter frequency here and the digital filter frequency, remember the purpose of this equation here is to solve for the constant C. So we know that omega here, capital omega, is equal to 2 pi f divided by f of S, where this f here is the digital filter frequency cutoff. And this is equal to 0.5 pi if we substitute in our digital filter frequency cutoff and our sampling frequency cutoff. Because as from the question, our digital filter frequency cutoff is 3 kHz. And our sampling frequency cutoff is 12 kHz. So 3 divided by 12 will give us a quarter. And then we multiply that by 2. So we get half that of pi. Now that we have capital omega here, it's possible for us to solve for C. Now remember, in this particular case, we have f of a on our equation here. And we know that we were given omega of a. So we know omega of a equal to 2 pi f of a. So f of a here is going to be 2 pi divided by omega a. Oops. Yeah, I wrote that wrong side. Now I'm watching back my equation here. Go to omega a divided by 2 pi. Sorry for that. Right. So, and then if we backtrack a little bit, we see that omega a here was 4 radians per second. So we do the substitution here as required. And we can solve for C, which is going to be essential for us to go proceed with the bilinear transform. So in this particular case, we can see that C here will resolve to an integer value of 4. We put this into our S equation, which is S equals to C multiplied by Z minus 1 divided by Z plus 1. And we do the substitution here into the analog filter prototype to transform this H of S equation into H of Z. after we do our substitutions and simplifications and so forth, we will get h of z in this form here, which is 3 multiplied by z plus 1 all squared, and then we got a quadratic on the denominator here. But please note this is the anti-causal form because we only have positive powers of z here. We need to transfer this into its causal form by multiplying by z to the -2 on the numerator and the denominator here. And then if it as required, if we need to transfer this into standard form, we take the constant term on the denominator after we transfer this h of z into its causal form, and then we divide the numerator and denominator by that constant term, which is why we have this 1 here on the denominator. So depending on how the question asks for the answer, it may be that it says, okay, just solve for h of z. If it just says solve for h of z, the anti-causal form is quite fine. If it says it needs the causal form, you need to do the multiplication where you transfer this from positive powers of z into negative powers of z. And if it asks for the standard form, you go one step further and then you take the constant term on the denominator, which doesn't have any powers of z associated with it, and you divide the numerator and denominator by that constant term in order to get this into standard form. So pay particular attention as to what the question is asking for these transforms. Because if it asks for you to express your answer in anti-causal, causal, or standard form, it means that you will be required to do some additional steps in order to get towards the final answer. If it doesn't state any, the anti-causal form is perfectly fine. So there will be nothing wrong with that. Now, analyzing the magnitude and phase response, please note this is not required for your exam. This is just for illustration purposes and for design purposes for anyone who may have to design digital filters at this point. Note that the magnitude response and the phase response here are both non-linear in nature because of that analog filter frequency mapped into the digital frequency. And that's especially true because of the warping effect that we observed. However, if we compare the magnitude response between the analog filter here and the digital filter, we see that it's quite similar with just a few little shifts accordingly. So it does a very good job in mapping the magnitude response for the analog domain to the digital filter domain. And we can see here in particular that if we watch our cutoff frequency, which was 4 radians per second here, we see that it maps to our required digital filter frequency cutoff, which is 3 kHz here accordingly. If we analyze the impulse response, we see that for about 10 sample periods, we basically have a good response as required for our digital filter frequency, for our digital filter design, sorry. And you take after these 10 samples will just end up being 0. If we need to draw this as a canonical representation, we have our Z domain equation, and we saw from lecture 14 how to go about doing the canonical representation. Just use the standard diagram representation for the canonical and substitute in your components as required for this particular visual representation. Now, the bilinear transform that as we saw here and the impulse invariant design technique works for low-pass filter designs. However, it's possible to use the bilinear transform here to design for a high-pass filter design. And typically, we don't use the impulse invariant technique to do this mapping of a low-pass filter to a digital high-pass filter because of that stability criteria that we observed in Monday's lecture. And as of such, when you do this mapping using the impulse invariant design technique, you get poles outside the unit circle and you get poles on the right-hand side of the S-plane, which basically means your designs are going to be stable-minded. However, the bilinear transform, because you're matching the frequency response of the filter, it does allow to map any analog low-pass filter design to a digital high-pass filter, but you're going to have to do a small modification for 2 of the equations. So in the low-pass version, meaning low-pass analog to low-pass digital, our S equation, our f of A equation is given by C z-1 divided by z plus 1, and in this particular case, it's going to be the tan version. But when you go from low-pass to high-pass, being a low pass analog to a high pass digital, this part here for S is going to flip. So it's going to be S equals to C Z plus 1 divided by Z minus 1. And our f of a equation now becomes negative C divided by 2 pi cotan of 0.5 pi. And if you remember your trigonometric series, cotan of x is basically just 1 divided by tan of x. So you can use this mapping here accordingly to solve if you are required to design a high pass filter from a low pass analog filter prototype. So just remember the key differences here, depending on what the question asks you for with respect to your design. Now for your own practice, I want you guys to repeat example 1 here from this lecture using a high pass filter of the same cutoff frequency. And I have given you guys some of the work in here to begin with. So we know that we're using this analog filter equation here as of such. The omega here will still resolve to the same thing as required from the low pass version. We can solve for C here, and we're going to see that it's going to be minus 4. And then we can do the substitution into H of S here for our high pass filter design. And we see we get our H of Z equation here. And we can transfer this into its causal form. And then we can standardize it into the standard form. So for your homework, because I'm giving you the answers here for verification, attempt to do this using the high pass filter design instead, and see if you can get these answers. And this will actually give you some good practice as to the type of questions that you will expect using the bilinear transform for your final exams in particular. And analyzing the response of the high pass filter, we see that's just going to be the complete opposite of what we saw for the low pass filter. So whereas the low pass filter went from 1 here down to some constant value, the high pass filter design will start from 0 and it goes towards some constant value on top here as required for the magnitude and phase. And we can see basically the comparison between the two here. Alright. So that brings us to the end of our first lecture for today, which is basically showing how do we use the bilinear transform to map the frequency response of an analog filter prototype to its required digital filter design. We also saw that in using the bilinear transform, by using the analog filter equation for the frequency, and we need to know what's the digital filter frequency, that's going to be our cutoff. And the sampling frequency, we are able to solve for the constant term C. Because we have this constant term, depending if it's the low pass version or the high pass version, we'll be doing the substitution for S, which is C Z minus 1 divided by Z plus 1 for low pass, and then the opposite for high pass. We do the substitution into H of S, make it in terms of H of Z, and then we basically are somewhat finished with our equation as required for a digital filter. Depending on what the question asks you, if it's okay to leave it in anti-causal form, you can leave it there. If the question asks for the causal form, you transfer from positive powers to negative powers of Z. And if it asks for the standard form, you're going to use the constant term for the causal form on the denominator and divide the numerator and denominator by this constant term in order to get it into its standard form. We also saw that in doing the design for a low-pass filter, analog filter prototype into its high-pass digital filter design, the S equation and the S equation and the F of A equation are modified. So just pay particular attention to what the question is asking for. If it's going to be a low pass filter design or a high pass filter design, remember that S equation and the F of A equation, they are going to be changed depending on what the question is asking. All right. So are there any particular questions regarding the material for this lecture? Alright, doesn't seem like we have any questions. Alright, so let's move on to the IIR filter examples in particular. Ink annotations here. 20. Alright, so this lecture here basically is just going to give us an idea of the type of questions that we can expect for IIR filter designs and how we can go about doing these questions in particular regarding the impulse invariant design technique and the bilinear transform techniques. So remember, in order to do the design for an IIR filter, we also always will require to have the analog filter prototype equation. And then, depending on what the question asks, we use one of these techniques here. We saw from Monday's lectures and today's lecture how to go about doing these techniques in particular. So let's start with requirements design that we are going to have to use for each one of these techniques here. So we have to design a 10 Hz digital filter. So we are already given our digital filter frequency cutoff based on a 10 Hz 2-pole Butterworth filter. So this 10 Hz here is going to be our analog filter frequency cutoff. And we have the sampling frequency, which is 100 Hz. So we already have our 3 frequencies as required for each one of these techniques. We're also given the analog filter equation here as required. And we're going to start with doing our impulse invariant design technique. So as we saw for the impulse invariant design technique, this means that we need to go back from h of s into h of t by doing the inverse Laplace transform. So we can do partial fractions here, and we see that we'll get imaginary values. And one thing to note is that once we start getting imaginary values because of the partial fractions, or when we try to factorize the denominator here, it's just a lot faster if we just complete the square in order to get the equivalent transform. However, I'm giving you guys a nice Laplace transform here for imaginary values that you can use as required. So if you want to use this transform, that's fine. If you want to complete the square like normal, that's also fine as well. So in using that Laplace transform, we get h of t in this form here. And we have our h of s in partial fraction form here. So we can just compare. We just see that c here is going to be 0, d is equal to 44.4. And omega naught was 44.4 as required, and a was 44.4. I'm watching the form here to see how it doesn't map only. So we can just do the substitution here for h of t. And we get h of t immediately from using that Laplace transform representation. Because we have h of t, we now need to get this into h of nt. Because this is in continuous time, we need to go into discretized time as required for the impulse invariant design. So we had the sampling frequency, which was 100 Hz. So t is just going to be 1 divided by that 100, and we can substitute that in for every part, but that we have t here as accordingly to get this into h of nt. In doing the substitution, and now we have h of nt here, we can transfer this h of nt into h of z using the z transform tables. And we see basically h of nt matches a of n here, given by this exponent, and sine of b of n here, u of t. So we have our equivalent h of z transform from the z transform tables. And we just do the substitution to a and b accordingly for our constants, and we get our h of z equation as required. Now, typically the question ends here once you have the h of z equation in its causal form. The graphs here is just for design considerations to see what does it look like to match the analog and digital filter magnitude responses. And as of such, because we see here that the amplitudes on the y-axis here are quite different, we just amplitude scale accordingly. So we just approximately divide the h of z by 100 to get it matching back to the required amplitude. If you want to do the design in MATLAB, these are the commands to go about doing it. Now we're going to use the same analog filter prototype here. and the same frequency requirements to do the bilinear transform now. So we know the general design steps where we have the analog filter equation. We need to match the analog filter frequency to the digital filter frequency. Calculate for C here, and we substitute for S using the bilinear transform. Now, note in this particular case, because it's a 10 Hz IIR filter, this is basically going to be a low-pass filter design as required, unless otherwise stated in the question. If the question explicitly says use a high-pass filter design, most of the times you are going to be designing for the low-pass filter design variant. If you're unsure, feel free to send us a question and we can resolve that immediately if there's something that requires clarification in the final exam. Alright, so we just basically follow these same design steps for the bilinear transform as required. So we start with our analog filter equation f of a. We know f of a here is going to be 10 Hz, and we know that our cutoff frequency for the digital filter was 10 Hz as well. So we can solve for capital omega here, which is 2 pi fc divided by f of s, at 0.2 pi. Substitute this in, and we can make c the subject of the formula, and we get c here is equal to 193.3. We substitute c here in for the s equation as required, and then we substitute s to get h of z. We'll see here that we get some improper fractions on the denominator, so that means we're going to have to multiply the numerator and denominator by z plus 1 all squared. And I'm going to leave you guys to actually do this completion here, as practice, to go about solving for this. See if you can get this particular equation into its causal form. The anti-causal form I'm giving you here for verification is given by this h of z equation, and the causal form for verification is also given by this block here. So for your homework, attempt that question and see if you can do the working to get the anti-causal form here and the causal forms. If you need to express this in standard form, we basically see that the constant term here on the denominator is 58518, so we're going to have to divide the numerator and denominator by this term here. In standard form, we see that we'll get this required equation. For design considerations, if you want to plot the graphs, normally at this point here, once you have the h of z, that's the end of the question. Plotting the graphs is if you're going to be doing some design work afterwards. We basically see that the analog being the red graph and the digital being the blue graph here. We want to have a nice close match. And the bilinear transform does automatic scaling of the amplitude responses or the magnitude responses for us, so we don't have to worry about that afterwards for the design. If you wish to do the bilinear transform in MATLAB for the filter design, this is some example code here for our question that we just loaded. Alright, that basically brings us to the end of our second lecture. And you can see basically once we know the design steps, it's very straightforward as to how we go about solving for the IIR filter designs using the impulse invariant design or the bilinear transform technique. And once you know these steps in particular, it's just very simple to go about doing the substitutions and inverse transforms and so forth from Laplace to time to z, and doing the substitutions as required for s to go into z and whatnot, depending on which design technique you're using. Right. So are there any particular questions about anything that you guys are unclear about using the impulse invariant design technique or the bilinear transform technique? Alright, doesn't seem like we have any questions at the moment regarding this. So hopefully you guys do understand what we did for this IIR filter design and whatnot. And once we start doing practice questions and whatnot and so forth, if you guys do encounter any problems, feel free to send them my way to resolve those problems for you guys. That's alright. So let's move on to problem set 3 here. Let's see which questions you guys voted for on the poll. Alright, so from the poll here, we see that question 2, question 5, and question 6 here, those were the ones in particular that you guys want me to do live. So I'm going to do these in order as we're going about. Right. I'll promise a 3. Maximize this up. So question 2 here basically says examine figure question 2, what is h of z and what type of transfer function realization is this? So let's go about analyzing this in particular. I got my whiteboard here. Look back this question. The figure question 2 here is given by this block diagram, and we're going to have to figure out how do we go about solving for our z equation as required. So I'm going to have to do a quick sketch of this diagram here, and I'm going to transfer this onto the whiteboard, and then we're going to use some intermediary signals in order to assist us with solving for our y of z equation as required, and our h of z as required as well. So, alright, let me do my sketch here in particular. On side. Inputs here, what you can say is z. Carry this across. 3. Transformation junction. Carry this across here. 5. Output z. Go down here. 1. It was 10. Another summation junction. Another summation junction. Negative. Triangle. 6. To the -1 block. Okay, so let's draw in the next set to the -1 block here. Three up to a summation junction. Positive, negative. 5. Put it on another z to the -1 block here. Alright, nice. So, and doing our design here, I'm just bring this back across. Connect this here. We're going to have to define some intermediary points as required for us to actually do our analysis. So I'm going to watch at the output of each one of these summation junctions here. I'm going to do all these in terms of W. So let's say here is going to be W1, and here will be W2. This one here is going to be W3. This one here is going to be W4. Need any more? No, I didn't need any more. All right, and then for each one of these junction points here, I'm going to just put in my delay level so that way I don't get confused. So this one here is going to be z to the -1 x of z. And this one here is going to be z to the -2 x of z. And this one here is going to be z to the -2 y of z. This one here is going to be z to the -1 y of z. Alright. So I want to start with W4 here. And analyzing what W4 is here, we see that if we watch our two inputs into the summation junction, we have z to the -2 x of z multiplied by 3, and we have 5 of z to the -2 y of z, and this is an add and a minus. So we basically write our equation here for W4 being such that it's excuse me, 3z to the -2 x of z minus 5z to the -2 y of z. Alright, so now that we have W4 here, let's go about watching for W3. So W3 here, if we watch the two inputs, we have z to the -1 x of z by 10, and we have W4 coming in here to give us W3. So W3 here is equal to W4 plus 10 z to the -1 x of z. Alright, so that basically takes care of this summation point and this summation point here. Let's go up to W2 now. So W2 here is the addition of W3 minus 26 z to the -1 y of z. Put that in. W2 is equal to W3 minus 26 z to the -1 of z. And then let's just watch W1 here, because now we have these three summation points already covered. So W1 here is the addition of W2 plus 3x of z. So 1 is basically W2 plus 3x. And then we just need our y of z equation here, because we already covered the summation point here for the output. So y of z is going to be 5 of W1. So if we do all our substitutions here as required, we can get y of z here. So actually, let me do these substitutions. Alright, so we have a W3 of equation here. So this here will transfer to the 3z to the -2 x of z minus 5z to the -2 y of z plus 10 of z to the -1 x this one here, because we have W3, is going to be this entire equation here. I don't want to have to rewrite all of this, so I'm just going to use different inks. So this here can go here, and W3 is positive, so we just add in 26 there to the -1. Then W2 here is also positive, so then we have add 3 x of z, and then we have y of z here just multiplying by 5. So if we take this entire equation here that we formulated in all our w's, and we put this here into our y of z equation, what we will get here, y of z equal to 15 x of z plus 5 into 3z to the -2 x of z, change in square brackets, minus 5 z to the -2 z. Just going to check this back just to make sure. Yeah, I'm checking that back just to make sure. I'm grouping all my z to the -2s here, and now I'm going to group my z to the -1s, plus 50 z to the -1 x of z minus 130 z to the -1 y. Just finish expanding this out. So this is going to be 15 z plus 15 z to the -2 z minus 25 z to the -2 y of z plus 50 z to the -1 x of z minus 130 z to the -1 y. Right, let's carry all the y of z's onto the left hand side and put all the x of z's onto the right hand side, and have y of z here into 1. So add this 1 here for that. This here is going to be plus 25 z to the 2. And then we had negative 130 z to the 1 here, so that's going to be positive z. Positive 130 z to the -1. Group of our x of z's here. 15 plus 15 z to the -2 plus 50. Let's make sure this is correct. 15 here, 15 z to the 2 plus 50 z to the -1. And then if we rearrange this such that it's going to be y of z divided by x of z, which is basically giving us our transfer function, this is going to be 15 plus 50 z to the -1 plus 15 z to the minus 2 divided by 1 plus 130 z to the minus 1 plus 25 z minus 2. Alright, so that basically gives us our transfer function here using the block diagram representations for question 2. Are there any particular questions regarding the method or how we went about doing this? Alright, looks like we're fine. Okay, let's move on to question 5. So question 5 was design an enter moving average filter where the first null point is at 100 Hz and we're using a sampling frequency of 500 Hz. Alright, so question 5 is pretty straightforward. So this basically is the moving average filter design that we'll be doing in particular. Let me label these. Three, 2, is 5. Alright, so for the moving average filter design, we need to know what's going to be our zero crossings. So our zero crossing is given by capital omega here, which is 2 pi divided by n. And we know pi here, capital omega, the function of common omega multiplied by that sampling time, which is going to be 2 pi divided by n. So we can make common omega here the subject of the formula, which is going to be 2 pi divided by nt. N here is equal to our sampling frequency divided by our first null frequency as given by the question. So the first null point here was at 100 Hz. So that's here, it's going to be 500 divided by 100 equal to 5. And because we know n here is going to be 5, that means we can create a moving average filter with 5 terms. So y of n here is going to be 1 divided by 5 into x of n plus x of n 1 plus x n minus 2 plus x of n minus 3 plus x of n minus 4. Brackets here. Right. So because we have n here, which is 5, that's going to be 1 divided by n here, and then the number of terms inside this brackets here needs to be 5 terms. So this here is going to be first, second, third, then fourth term, and then our fifth term. In order to make sure that it averages out as required for a moving average filter. Right. So that's pretty straightforward for question 5. Anything that requires some sort of clarification regarding this? It doesn't seem like anyone needs any clarification regarding this. Alright, so let's go on to question 6. Alright, so question 6 here was basically to repeat the design of question 5. We're going to be using a 9-point Hammond window, FIR, and a 9-point triangular window, FIR. And to use the FDA tool to design the filters above. So unfortunately, because I don't have MATLAB on this broadcasting computer, I won't be able to do part 3 for you guys. But you did see how to go about doing the design for the FIR filters using the example code in the lecture that we just now did. So I believe there are also some example MATLAB code as well to go about designing the filters as well and so whatnot. But if there aren't any example code, I will do the example code on my computer that does have MATLAB, and I'll post it up for you guys as well, so that way you can see how you can go about doing that. So I'm just going to focus on doing the design for the 9-point Hammond window here and the 9-point triangular window as required. Right, so I'm not sure if I might not need a mic board here at this point. I think I just automatically generate these, if I'm not mistaken. No, I'm still going to need a whiteboard here because I'm going to have to do a little bit of design stuff. Alright, so let's see how I'm doing this. Right. So for part 1 here, we're going to have to design for h of n, which is going to be our window, where fc here is 100 hertz. And for the Hammond window, Hammond or Hannon? Check that back. Hammond window, right. So for the Hammond window, the h of n equation takes the form such as 2fc divided by f of s, and we had f of s here equal to question 500 hertz. Think of 2 pi n c fs. Now I'm just going to bring back up all my lectures here to check back the equations that we're actually supposed to use, because I did advise you guys not to use the sink equation. It was to use the other equations as required. Let's see. Oh, where was that lecture? This. That's that. Just give me a second, guys. I was looking for the lecture where I actually did that design. Right, there we go. Right, so remember, you don't want to use this equation here. It's still correct, yes, but do not use the equation that you do want to use, h of n equation here, which is equal to sine of 2 pi n fc divided by f of s, all divided by pi of n. Right, so that's the equation you want to use for h of n. Alright, so in our particular case, because we're designing for how many points, I'm going to have to figure that out. So a 9-point timing window, right? So 9 points means n here from -4 to 4. Right, so we have that. Okay. So, okay, one thing I need to clarify here. This h of n equation here is for our filter. That will be the ideal low-pass filter response. So, we're doing the design here for question 5 using a 9-point Hamming window based IIR filter. But that means we need to have the filter equation first in order to get our sample points for the filter, and then we can apply the Hamming window on top of this. So this h of n equation that we're dealing with here is the ideal low-pass filter response given by this generic equation here, which is h of n sine 2 pi n fc divided by fs all divided by pi of n. So we need this h of n first, and then we can calculate out for our window function for the Hamming window. So we know w of n here is equal to 0.54 plus 0.46 cosine of 2 pi n divided by n minus 1. And capital N here was 9. So we're going to calculate out for h of n here first, and we're going to use Octave here to go about doing this. So I see I got one question here. You can use MATLAB to solve questions in the final because, like I said, the final is open book exam, so you're able to use MATLAB as required. I don't expect you guys to like to do all the long calculations for this h of n and whatnot and so forth. But like things for like the Z transform equations and anything else that you can work by hand, in particular like resolving equations and any sort of longhand working, like if it's long division and so forth, I do expect you guys to do that by hand and not automatically. Same thing with the partial fractions. I know there are automatic partial fraction solvers online, but you are required to show the working for the partial fractions. If it's something like a numerical method evaluation, like for this h of n or for this w of n, you can just use MATLAB accordingly. Just write down the equation for h of n and w of n, and then you can write out the vector values for h of n and w of n as a result from MATLAB as required. So I'm pulling up Octave here to help me resolve this. Yeah. Okay. I'm going to need to define my n vector. -4 to 4. And I have an h here, so I need my fc and my fs. Fc here, question was 100 and ffs was 500. U 100, f of s was 500. Right, and then I can solve here for my h equation. So we're not using the sync one here. We want to use this form here. Right, so h is equal to sine of 2 by pi by n by fc divided by fs. I'm going to leave the pi of n one side for the time being. Right, and then that was h, let's say h2 here, h divided by pi by n. We see here if we do this, it's not going to work as required because of some weird scaling and so forth. So we're going to have to do pi dot star n. Nope, that didn't work either. What did I do? But all right, so not dot star is dot define. Right, there we go. No, you're not going to be required to plot anything for the final using MATLAB. Once you have your equations, that's it. There's not going to be any plots, so you don't have to worry about that. All right, so we get our vector values here for h as required, and we see that we have one that's not a number. Just remember when you get this one which is not a number, this was going back to where we had two fc on fs sync parts here. So we're still going to have required to calculate this two fc on fs here. So I'm just going to do a quick calculation here for this. This is 2 by 100 by 500, 2/5, which is 0.4. I'm going to use that 0.4 here for where we had that not a number, because that's basically going to be a limit evaluation. Because basically once we have sync of x being sine of x divided by x, and if we limit evaluate this limits as x tends to 0, means that this just goes to 1. So we're going to need this 0.4 here to do our evaluation as is. So we can say from MATLAB or Octave, h of n here is equal to, I'm just going to bring aside my Octave, I can copy these down. Right, there's going to be minus 0. I'm truncating to 3 decimal places. Right, so 0.076 and then minus 0.062, 0.0 0.303. The one that's not a number, so this one where we have is not a number, that's going to be the limit evaluation that I just now did. So that's where the limit evaluation of that is just going to be 1, and I calculated for that being 2 FC on FS, which is 0.4. So I'm going to put in 0.4 here as required. 4. Then we have 0.303 because of the mirror effect by using these things. 0.04, negative 0.02, and minus 0. Alright, so for me to replace this not a number here in Octave, so this comes like if we say h2 of 5 brackets. Alright, so this is like if we say h2 of 5, because this is like 1, 2, 1, 2, 3, 4, 5 here, right? So I'm going to have to replace h2 of 5 here with our limit evaluation, which is 0.4. So when I call back h2, in this particular case, I'll have this 0.4 here so I can go about doing my calculations as required. Alright, so now that we have our h of n here, which basically was our filter, we need to go back to solving for w of n here, which was 0.54 plus 0.46 cosine of 2 pi n divided by n minus 1. So we're going to be solving for this in Octave as well. So we can have w here is equal to 0.54 plus 0.46 multiplied by cosine 2 by pi by n divided by n minus 1, which was 9 minus 1. And we get our w here as required to go about doing this. So we have our w vector here for all our values for w. So I'm going to just bring this across here, and let me just write down my w vector. The w of n here is equal to 0.08, 0.215, because I'm truncating into 3 decimal places, 0.4, 0.865, 1, and then we have the mirror effect, 0.865, 0.54, 0.215, and then 0. Right. And the last thing we have to do here is that basically we just have h of n by w of n, which we just basically take each one of these values here and we just multiply them straight across. So we have h dot star w, and we get our multiplications as required straight across for each one of these. Now, I don't get, for some weird reason, we got 0 here. So I'm just going to verify this. Oh, sorry, I used the wrong one. So this is h2 here, star w. And so you see, we're going to get some like really weird values here because of the decimal places and whatnot and so forth. And Octave here will just do the truncations for us. So this comes like if we take our values here from our equations as of such, because we have truncated values here, and we're just going to be multiplying them across. So I'm just going to do for this one here, negative 0.076 and 0.08 to show you guys what this does look like in Octave. So negative 0.076 multiplied by 0.08. And you see here we get like a truncation here. And that's just basically telling us, okay, the answer here is up to 10 to the negative 3. So let's see if I had something here that I can go about doing this. It isn't the setting here. So I'm just going to use this as required, as we see here for h2 and w. So I want to just bring this back across here. And I'm just going to write these answers out instead of in the truncation form. We're going to expand them out. So first answer here was negative 6.054 by 10 to the negative 3. This here is going to be negative 0.006054. So I'm going to write this out in full form here from using our answers. But you're free to put these down into 3 decimal places or 3 significant figures. In most cases, significant figures will be better to use. So we can see here, in this case, this is going to be 6.5. The next one here is going to be minus 0.0134 from my approximations. Alright, next one here is going to be 0.0505. The next one here is going to be 0.262. This one here is going to be 0.4. And it's a mirror effect at this point, so we don't have to worry about any truncations. So it's just 0.262, 0.05, negative 0.034, and negative 0.00605. Right. That basically brings us to the end of our first part here, our question. And then the second part of the question was basically asking us how to do this for the triangle waveform, if I'm not mistaken. All right, the triangular window based IIR filter. So we're going to have to use the triangular window from our lecture 16 here, which I brought up to see how to go about doing the question in particular. Oh, well, let's see if I can find, not lecture 16, sorry, lecture 9, which had the equations. So from lecture 9 here, we had our triangle window equation, which was W of k is equal to 2 of k minus 1 divided by n. And k was going between 1 to k to n divided by 2. But in our particular case, we're going to be using 2 of n minus k plus 1 divided by n here, where we're going in the range of k here in order to get this. So k is going from n divided by 2 plus 1 to that of n. So in our case here, let's see how I'm going to win this in Octave. So bring this back across there, our triangle window. And that there. Then in our particular case, bring Octave back here. So we want to be doing W of t here, which is our triangle, but we're going to need k first. So let's say k here. So we had n, which was 9. So that's 9 divided by 2 plus 1. It's 5.5. And we're going up to n, which was 9. So, okay. Right, so W of t here is equal to, okay, I'm just going to use my n vector here, and let's see what's going to happen. 2 by n plus 1 divided by 9. Right, so yes, that should work as expected. Alright, we got 9 values here, but we only have to use 8 of these values as required. 8 values? No, we only have to use 9 values as required, right? That's correct. because we have 9 values for our h of n, if I remember correctly. So 2, h2 had 9 values. Right, nice. So for a triangular window, we just say w of t is equal to 2 multiplied by n minus 1, 2 by n minus 1 divided by 9. Because that's 2k minus 1 divided by n, where n here was 9. So we have a w of t here for a triangular window, and we have our h here as required. Now, one thing to note here is that this sequence of values here, it's not going to be symmetric as required, because we have this -1 that's appearing here in particular, and that's going to throw off our equation regarding our calculations. So that's perfectly fine if we get in some throw off here, because remember the triangular window only operates on even values. In this particular case, we're dealing with odd values. That's fine. That's not very much of an issue. So then, in order to complete this, we just say wt dot star h2, and we get our final answer here for the triangular window function as required. Alright, so that brings us to the end of our questions for problem set 3. So like I said, for part 3 here, I don't have access to use the MATLAB on this broadcasting computer to use the FDA tool. So I'm going to do this offline if the code isn't provided, and I'll provide the code for you guys as to how to go about doing the filter designs with these 2 points here. Right. So are there any other particular questions regarding our lecture so far, or regarding the course material and whatnot? Anything you guys need to ask about the midterm or the final exam and whatnot, feel free to ask now. Final exam is going to be around a 12-hour window, from what I remember. So it's the same sort of format that you will get from previous final exams, where you're going to have 5 questions to attempt. And we're giving you guys a 12-hour window in case of any communication issues or any power failures or whatnot, so that way you guys can go somewhere that does have power or internet in the event of those that whatever happens. Will we be testing on what came for the midterm? Traditionally, no, but I can tell you for this particular year, one of the topics may repeat on the final. There normally isn't really much hints to give for the finals, because like I said, this course is pretty straightforward. So once you actually do your past papers and so forth, especially like the more recent past papers, you will get a lot of preparation as to how to go about doing the questions for this year's final exam. I will post up a couple of the past papers regarding the final exam itself, for what I can actually post up as required by the university. The more recent past papers, I'm not too sure if they're on the library website. I can check right now, so I'll update one side. Yeah. Here. Okay, so the library website only has it up to 2014. But that's fine enough, because I believe up to the 2014 paper, yeah, up to the 2014 paper you had some good experience, and the questions basically are the same format and whatnot, so you'll be perfectly fine. Some of the past papers I'm going to put up, there's also going to give you like the types of questions that are going to be very similar in nature as to how you're going to do about these questions in the final exam and whatnot. However, I can't put up the more recent past papers due to legal considerations and because of the university restrictions. So until they do go up on the library website, I can't really do anything else. The only advice I can give you is if you can find someone who did the course last year, or if you can get access to the past papers somehow else, feel free to go about getting access to them. But legally on my side, I cannot put up those past papers on the My Learning course shell. I can only put up what was provided by the library or anything before the years provided by the library. I can tell you what I can put up regarding those though, if I do have them here. Okay, I probably don't have them here. Let's. I'm still active, right? Let's check. So I will put up past papers from the year 2009 to 2013. I saw the library website has up to 2014, but the selection of questions in those past papers are sufficient enough to give you guys enough preparation. You will see that in those past papers, there are topics that I did not teach because the last lecture, which is what we're doing on Monday, it's going to be a specialization lecture, and that lecture basically gives you the information for the final question in your final exam. So when you're going through the past papers and you see these odd topics and you know that I definitely didn't teach you these, just skip those particular questions or particular parts of questions. Because like I said, I didn't teach you those, so those sort of questions won't come on the final exam for this year. But Monday's lecture is going to be our last lecture, and it's going to be extremely important because the information in that lecture is going to be the information you use for that entire final question in your final exam, which is going to be 20 marks over the 100 marks. So make sure you ask a lot of questions in that Monday lecture in particular. Right. Any other further questions? It doesn't seem like we have any further questions. One thing to note though, I knew for your midterm that you guys were allowed to do digital ink if you wished, such that you can write on your tablet or stylus for your attempts for the midterm. However, for the final exam, because of the new exam regulations, and I don't know if they have been updated as yet, but now what I do know is that you're going to have to require to write your answers on paper and then take images and compile that into a PDF and send. They will not allow you guys to actually use digital ink as yet because it's not in their regulations. I did make a suggestion last semester to forward it to the exams council to allow for this, but I'm not sure if it got approved in time as yet. So if it did get approved in time, I'll check back the exam regulations and let you guys know. But for now, when you're doing your final exam, you will actually have to do it on pen and paper and then take photographs of those and compile the PDF and for submission and so forth. Alright, so if there are any further questions, feel free to leave them down in the comments below, or you can directly email me if you wish. And remember, next week Monday is going to be our last lecture. You will see on my learning that you'll see DSP examples 1 and 2. That's just for further reading and for anyone who needs to do design considerations and so forth. But you will not be tested on DSP examples 1 and 2. The lecture that we will be doing on Monday, which is our last lecture, is going to be named Audio Fingerprinting, which is an example of how DSP is applied to a practical application. So try your best not to miss Monday's lecture because that's our last lecture. And like I said, the material for that lecture is based on the final question in the final exam. Yes, you should be able to sign the plagiarism form electronically. I don't foresee any problems with that. So long as it is an ink signature and not a typewritten signature, that should be perfectly fine. If not, just print out a plagiarism form and just sign it as well. But like I said, an ink signature for the plagiarism form is fine. Cannot be a typewritten signature. All right. So like I said, Monday is our last lecture. You want to see DSP examples 1 and 2 posted up on the My Learning page, but remember the material for DSP examples 1 and 2 is not going to be tested. That's just for your general information or for any design information that you require. The lecture on Monday is going to be named Audio Fingerprinting, and that's a DSP example on what is more practical and how to use those DSP techniques for an actual practical application. And that's going to be the material for your last question in your final exam, which is going to be worth 20 marks out of the 100 mark. Try best not to miss that lecture in particular. All right. So, like I said, leave any questions down in the comments below or directly email me. I'm perfectly fine with that. And until Monday, take care, be safe, and I will see you guys soon. Later.